So we are now on general exponential function. So this time the base of the expression that has the exponent is not an exponential function, but rather a constant. This a is a constant. It could be 1, 2, 3, 4, as long as it's not negative. It could be 0.2, it could be 1/2, it could be 1,000, 1,000,000, as long as it's not negative. Okay, because you see here in the formula that whenever you have a constant raised to u, du, the integral of that will be the given exponential expression divided by the ln of a, the constant here which is raised to the u. Now, you can only have this answer if the derivative of the u is complete here in the du. So the derivative of the u is du, and as such, then you can write the integral of this as au over ln of a. Okay? Or 1 over ln a raised to u. Now, if you're going to apply that principle in here on our first example, we apply the formula, you could see that this is your AU. So your A is 5, you can see that, and your U is x squared. So the next thing you do is, of course, if whenever you assign an expression or a function as a U, the next step always is you differentiate it. That's the next step always. Look for your u and differentiate it. So in this case, the derivative is 2x dx. You already have this x here and you have this dx here, so you only need the 2. So there's a need for you to multiply by 2 over 2. You place the needed 2 in here to go together with your x and dx and the 1/2 before your integral. And that's it. This is already your AU. So your integral will be AU 5 raised to x squared all over 1 over ln of A, where A is 5. These 2 here in the denominator together with the ln of 5 is the 1/2 that you have written before the integral. It's the thing that is not needed here in the process of integration because we only need the 2. So meaning we are still left with 1/2 in our 2 over 2 to account for. So that is 1 over 2 ln of 5. And this is AU. So this is your formula. And if you compare it, that's your AU. And this is your LNA. Okay? That's for exponential functions in which the base is a positive constant, not exponential. That is E, but rather a constant. Okay? Have another one here. Now, you have 3 cosine x, sine of x, dx. Of course, right away, you will see that this is your a raised to u. And just simply check if this will be your du. So, your a is 3. Your u is cosine x. The du is negative sine x dx. What do we lack in here? Negative 1. So, here, we place here. So, I'll place a dot here to show multiplication. So this is the negative 1 here, and this is the other negative 1 outside. So then this will just be simply an AU ln of A, which is 3. The negative here came from the negative 1 outside. So this is your A raised to U, and this is your 1 over ln of A, based on the formula that was shown to you a few minutes ago. Okay? What is good about this integrals class having an exponential function that is a constant is you would know right away that there's no other formula that you will use because it's unique in itself. You see right away that this is your AU. All you have to establish is the du of the u of your A, because no other function can process this particular integral other than the formula that was shown to you a while ago. Okay, so it's really an AU. Any question? Okay, where is the clearing part here? So we'll clear the markings. Now we go to the second to the last slide. The third example. The same thing with this class. In this particular example, this base is 3 and it's raised to ln of x squared. It follows that this has to be really a raised to u. Your a is 3, as you could see here, and your u is the exponent of the 3, which is ln of x squared. What's the derivative of ln? It's du over u. So what's the u of this ln? That's x squared. So it's 2x dx. What is its u? X squared. So you get to cancel this. You still have 1 left here. So it's dx over x. It's here. So meaning the expression here, dx over x, is actually the derivative of this u, which is ln of x squared. So it's there already. So your answer is, you only need to place in there the 2 in the derivative. So you need to multiply by 2 over 2. And the 1/2 you don't need to place outside. So 1/2 AU over ln of A, which is, of course, ln 3. Do you get it? So the way we deal with a general exponential function is forthcoming because of the presence of a base, which is a positive constant. So you know right away that the only thing that you will first try, hopefully it will work, is the formula for the general exponential function. Okay? Any question? Okay, now we'll go to the next. Let me just close this one. Okay, here, that's the last. This seems to be complicated, but no matter how complicated it is, always look for the most complex. This is already your constant base, so this tells you that this is your AU. Okay, so this is the complicated part. Okay, without this, you can actually have this integrated distributing the x e raised to x and the e raised to x in here. The x e raised to x can be solved using integration by parts, which will be another topic that we will discuss in the near future. Okay, so if this is your main function, the main function is a raised to u, a being 6 and u being xe raised to x, we know that this one is no ordinary differentiation. You will have to use here product rule of differentiation. Now, what is product rule of differentiation? First term, so if you get the derivative, the first term times the derivative of the second plus the second term times the derivative of the first. So this is the thing that you are seeing there. Now, both e raised to x is present, so you can have it factored out. So e raised to x times the quantity x plus 1. This entire expression is the derivative. And if you look very closely, class, on our given integral, here it is. Ano na siya ang derivative mo? E raised to x times the quantity x plus 1 together with the dx. It's this one here. So you see, it looks very complicated to the point that you won't really know how to deal with it at first. But actually, if you just choose the complicated and try to think of that particular function in which it will fall to and the corresponding formula, then you might find your way out in determining the answer to the given integral. So this entire thing is the derivative of this. So your answer is the given AU divided by ln of A, which is ln of 6. So that's it. So this part here is, if I may say, the simplest of the 3 parts of your module 3, which talks about techniques of integration. Now, do you have any question, class? Any question?
None, miss.
So I will clear my markings here. I'll stop sharing.